Welcome to Cosmos in a Pod Space and Astronomy Series, Episode 9. Get ready, because today we're taking a deep dive into the Big Bang. We're talking about the origin of everything, all the stars, galaxies, planets, even us.
It is.
It's a pretty massive concept, right?
And it's not just about understanding where we came from. The Big Bang model provides a framework for understanding how the universe has evolved, its structure, and potentially even its ultimate fate.
Okay, I'm ready to have my mind blown. But let's be honest, the Big Bang can feel overwhelming. Where do you even begin when you're talking about the beginning of everything?
We start with what we do know. We know the universe is expanding. We can see galaxies moving away from each other. And the further away they are, the faster they're moving. It's like rewinding a movie. If everything is spreading out now, it must have been closer together in the past.
So if we keep rewinding, we eventually get to a point where everything was packed together incredibly tightly.
Exactly. We call this starting point the singularity. It's a mind-boggling concept, a point of infinite density and temperature, where all of space and time were concentrated. Our current laws of physics break down when we try to describe the singularity itself.
So the singularity wasn't just tiny, it was everything. That's almost impossible to imagine. Then what happened? Did it just explode?
Not exactly. It's not an explosion in the traditional sense. Think of it more as an incredibly rapid expansion of space itself. Imagine a balloon with dots drawn on it. As you inflate the balloon, the dots don't move across its surface, but the space between them grows. That's a good analogy for how the universe has been expanding since the Big Bang.
Okay, I think I'm starting to get the picture. But what was it like in those very first moments? The source material mentions something called the Planck Epoch. What can you tell me about that?
The Planck Epoch represents the first 1043 seconds after the Big Bang. It's a period so early and so extreme that our current understanding of physics simply can't describe it. To put it in perspective, if the entire age of the universe were compressed into a single year, the Planck Epoch would be less than a trillionth of a second.
Wow, talk about a brief but intense moment. So basically, we don't really know what happened during the Planck Epoch. It's just a big mystery.
It is a mystery, but a fascinating one. Our current theories, like general relativity and quantum mechanics, which work beautifully to describe the universe on larger scales, break down at the extreme energies and densities of the Planck Epoch. It's thought that during this period, all four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single force. But exactly how they were unified and what new physics might govern this realm are questions that still elude us.
So it's kind of like trying to understand the rules of the game by watching only the last few minutes.
That's a good analogy. We can see the results, the universe we observe today. But those very first moments, the setting of the rules, are still shrouded in mystery.
It makes you wonder what kind of new physics might be out there waiting to be discovered. But as the universe expanded and cooled, things must have started to change, right?
Yes, thankfully. As we move beyond the Planck Epoch, the universe enters the Grand Unification Epoch. This period lasted from 1043 to 1036 seconds after the Big Bang. During this time, gravity starts to separate out from that unified force, becoming a distinct force in its own right.
So the first force to break away from the pack was gravity. What does that even mean? For a universe that's still smaller than an atom.
It's a crucial step. It marks the beginning of the universe differentiating itself, becoming less homogeneous, and setting the stage for the complexities to come.
Okay, we've got gravity doing its thing. What are the other forces? And what kind of stuff is even present at this point?
The remaining three forces are still unified. And the stuff at this point isn't atoms, or even the particles that make up atoms. It's a seething soup of elementary particles and their antiparticles. Things like quarks, leptons, and bosons. They're constantly colliding, annihilating, and being created in a frenzy of energy.
It sounds pretty chaotic. And then things get even wilder with the next phase, the inflationary epoch, right?
You're right. This is one of the most mind-blowing concepts in cosmology. During the inflationary epoch, which lasted from about 1036 to 1032 seconds after the Big Bang, the universe underwent a period of exponential expansion. We're talking about the universe increasing in size by a factor of at least 1026 in a tiny fraction of a second.
Okay, how can something expand faster than the speed of light? Isn't that like the ultimate cosmic speed limit?
It is, but there's a subtle but crucial distinction here. It's not the stuff in the universe that was moving faster than light. It was space itself that was expanding. Think back to that balloon analogy. The dots aren't moving across the surface faster than light, but the space between them is increasing at an incredible rate. since the speed of light limit applies to objects moving within spacetime, not to the expansion of spacetime itself. There's no violation of any fundamental laws.
So it's like the fabric of the universe itself is stretching faster than light. It's pretty hard to grasp. But why is this inflationary epoch so important?
The inflationary epoch solves a lot of problems for cosmologists. It explains why the universe looks so uniform on large scales, why the geometry of spacetime appears to be flat, and it provides a mechanism for the tiny quantum fluctuations that existed in the early universe to be stretched to cosmic scales, becoming the seeds for the formation of galaxies.
Wait, so those tiny quantum fluctuations, those random blips in the fabric of the universe, become the seeds for entire galaxies. That's incredible. It's like those tiny imperfections in a pearl that end up creating its unique beauty.
Exactly. And without this period of rapid expansion, those fluctuations would have remained microscopic, and the universe would look very different today.
So the inflationary epoch sets the stage for the large-scale structure of the universe.
Oh.
I'm starting to see how all of this fits together.
Yeah.
Okay, so after this wild period of exponential expansion, what happens next?
As the universe continues to cool and expand, we enter the Electroweak Epoch, which lasted from 1032 seconds to about 1012 seconds after the Big Bang. This is where another major shift occurs. The weak nuclear force, which governs radioactive decay, separates from the electromagnetic force. This gives us the four distinct forces of nature that we know today.
Okay, so the forces are separating. But what's the universe like during this time? Is it starting to look anything like the universe we know?
Not quite. It's still incredibly hot and dense, filled with a chaotic soup of elementary particles like quarks, gluons, and leptons. Think of it like a cosmic particle accelerator. But on a scale that's unimaginable, the universe is still smaller than an atom at this point. But it's teeming with activity.
So it's still a chaotic mess, but at least the forces are starting to fall into place.
Yes. And as the universe cools further, things start to get a little more organized. The next phase is the Quark Epoch, lasting from 1012 to 1006 seconds after the Big Bang. This is where the universe becomes dominated by quarks and gluons, the building blocks of protons and neutrons.
Ah, so we're finally getting to the ingredients for atoms. Does that mean atoms are actually forming during this epoch?
Not quite yet. The universe is still too hot and energetic for quarks to combine into stable protons and neutrons. It's like trying to assemble a Lego castle in the middle of a hurricane. The building blocks are there, but the conditions are just too chaotic.
Okay, so we have to wait a little longer for atoms to make their grand entrance. What happens next in this cosmic construction project?
The next stage is the Hadron Epoch, which lasted from 1006 seconds to about 1 second after the Big Bang. The universe has cooled down enough to a mere trillion degrees Celsius small to allow quarks to finally combine and form hadrons, which are particles made up of quarks.
Okay, so we finally have hadrons. What exactly are hadrons, and why are they important?
Hadrons are particles made up of quarks, held together by the strong nuclear force. The most familiar hadrons are protons and neutrons, the particles that make up the nuclei of atoms. So we're finally getting to the point where the building blocks of matter as we know it are starting to emerge.
So the Hadron Epoch is where protons and neutrons first appear on the cosmic scene. Does that mean atoms are right around the corner?
Well, almost. But there's a catch. The universe is still incredibly energetic during the Hadron Epoch, and there's a lot of antimatter around. When matter and antimatter particles collide, they annihilate each other, releasing a tremendous amount of energy.
So it's like a cosmic battle between matter and antimatter. Who wins this epic showdown?
Well, you and I are here, so obviously matter won out in the end. But it was a close call. There was a slight asymmetry in the early universe. A tiny bit more matter than antimatter. And it's because of this tiny imbalance that we exist today. All the matter we see around us, from the stars to the planets to you and me, is a remnant of this primordial surplus of matter.
Wow, that's amazing. We owe our existence to a tiny bit of leftover matter. So we've got protons, neutrons, and a whole lot of energy flying around. What happens next in this grand story of the universe's creation?
As the universe continues to expand and cool, we enter the Lepton Epoch, which lasted from about 1 second to 10 seconds after the Big Bang. The name comes from leptons, a family of elementary particles that includes electrons, muons, and neutrinos. During this epoch, most of the hadrons and antihadrons have annihilated each other, leaving behind a universe dominated by leptons.
Okay, so is this Lepton Epoch a key player in the story, or is it just a
Yeah,
brief interlude?
It's more of a transitional phase, but a crucial one nonetheless. The Lepton Epoch sets the stage for the next major event in the universe's early history, the Photon Epoch, where light finally takes center stage. But I think that's a good place to pause our journey for now.
I can't wait to hear about what happens when light enters the picture. We'll pick up right where we left off in part 2 of our deep dive into the Big Bang.
Welcome back to our deep dive into the Big Bang.
I'm ready to see some light. Literally. It feels like we've been traveling through a very dense, very hot fog for billions of years.
Well, you're not wrong, even though the photon epoch, which lasted from about 10 seconds to 380,000 years after the Big Bang, was dominated by photons, particles of light, the universe was still opaque.
Wait, and if the universe is full of photons, shouldn't it be bright? What was blocking the light?
The universe was still so hot and dense during this time that photons couldn't travel freely. They were constantly scattering off the free electrons that were abundant in the hot plasma that filled the universe. Imagine trying to see through a dense fog. The light keeps bouncing around and can't travel very far.
Okay, so even though light was present, it was trapped in this cosmic fog. What was happening within this foggy universe? Were any significant changes taking place?
Absolutely. Even though it was visually dark, a lot was happening during the photon epoch. Atomic nuclei began to form through a process called Big Bang nucleosynthesis. This is where protons and neutrons, which we talked about earlier, combine to form the nuclei of the lightest elements: hydrogen, helium, and trace amounts of lithium.
Wow. So the very first elements were forged in this cosmic fog. That's pretty amazing. But if the universe was still opaque, how do we even know that this was happening?
That's a great question, and it brings us to one of the most important pieces of evidence supporting the Big Bang model, the cosmic microwave background radiation, or CMB.
I've heard of the CMB. It's like a baby picture of the universe, right? But how does it relate to the photon epoch and the formation of the first elements?
Around 380,000 years after the Big Bang, the universe had expanded and cooled enough for a major change to occur. The temperature dropped to about 3,000 Kelvin, which is still incredibly hot by our standards, but cool enough for electrons to finally combine, with those atomic nuclei we talked about, forming neutral atoms for the first time. This process is called recombination.
So before recombination, the universe was filled with free electrons, which were scattering the photons and keeping things foggy. But once those electrons were locked up in atoms, light could finally travel freely. It's like the fog suddenly lifting.
Precisely, and those photons that were previously trapped, bouncing around in the cosmic fog, they were finally released, free to travel across the vast expanse of the universe. And those very same photons are what we detect today as the cosmic microwave background radiation.
So the CMB is literally light from the very early universe. We're seeing light that has been traveling for almost 14 billion years. That's incredible. But how do we know that this radiation is from the Big Bang and not from something else?
The CMB has some very specific characteristics that match the predictions of the Big Bang model. It has a nearly uniform temperature of about 2.7 Kelvin, and it has tiny fluctuations, hot and cold spots, that provide a wealth of information about the early universe. By studying these fluctuations, cosmologists can learn about the universe's composition, density, and even its rate of expansion. It's one of the most powerful tools we have for understanding the Big Bang.
It's amazing to think
Right.
that we can actually observe something from such an early epoch in the universe's history. It really makes the Big Bang feel tangible. So we have a transparent universe, the first atoms, and the CMB. What happened next? Did stars and galaxies start forming right away?
Not quite. The universe entered a period known as the Dark Ages, which lasted from about 380,000 years to about 150 million years after the Big Bang. This name can be a bit misleading because it wasn't actually dark in the traditional sense. There were no stars or galaxies yet, so there was no visible light illuminating the cosmos.
So it was dark in the sense that there were no stars? But what was there? Was it just empty space?
Far from it. The universe was filled with vast clouds of neutral hydrogen and helium gas, the remnants of Big Bang nucleosynthesis. And it was within these clouds that gravity began to work its magic, slowly pulling the gas together, setting the stage for the formation of the first stars and galaxies.
So the Dark Ages were actually a time of great potential, a time when the seeds of future cosmic structures were being sown. It's like the quiet before the storm.
Exactly. And as gravity pulled these clouds of gas together, they became denser and hotter. Eventually, the cores of these collapsing clouds became so hot and dense that a new process was ignited: nuclear fusion.
Nuclear fusion. That's the process that powers stars, the process that happens in our own sun.
Exactly. Nuclear fusion is the process by which lighter atomic nuclei, like hydrogen, are forced together under immense heat and pressure to form heavier nuclei, like helium. And this process releases a tremendous amount of energy, which is what makes stars shine.
So the first stars were born from these collapsing clouds of gas, powered by nuclear fusion. What were these first stars like? Were they similar to the stars we see today?
The first stars were very different from the stars we see today. They were much more massive, perhaps hundreds of times the mass of our sun, and they were incredibly hot and luminous, burning through their fuel much faster than modern stars.
Why were these first stars so much larger and hotter than stars like our sun? Was it just because they had more gas to work with?
It wasn't just the amount of gas, remember. The early universe was composed almost entirely of hydrogen and helium, the lightest elements, heavier elements, like carbon, oxygen, and iron, which are essential for forming smaller, cooler stars like our sun, were simply not abundant enough in the early universe.
So without these heavier elements to moderate their growth, these first stars grew to enormous sizes.
Exactly. They were true cosmic giants, blazing brightly for a few million years before ending their lives in spectacular supernova explosions.
Supernovae, those are some of the most powerful events in the universe, right?
Yeah.
What happens when a star goes supernova?
A supernova is the explosive death of a massive star. When a star runs out of fuel, its core collapses, triggering a shock wave that blasts the star's outer layers into space. This explosion is so powerful that it can outshine an entire galaxy for a brief time.
Wow, that's incredible. But what's the significance of these supernovae in the early universe?
Supernovae played a crucial role in enriching the universe with heavier elements. Remember those heavier elements that were missing in the early universe? Well, they were forged in the hearts of these first stars and then scattered out into the cosmos during those supernova explosions.
So the death of these first stars actually paved the way for the formation of stars and planets like our own. It's a cycle of cosmic creation and destruction.
Exactly. The heavier elements created in these first stars became the building blocks for the next generation of stars, and eventually, for planets like our Earth and for life itself.
So every atom in our bodies, every element that makes up our planet, it all came from the explosions of those ancient giant stars. That's a pretty mind-blowing thought.
It is. It connects us to the very early universe in a profound way.
This is also fascinating. But we've been talking about stars, and I'm eager to hear about the formation of galaxies. How did those vast collections of stars come together?
The formation of galaxies is a complex process, but gravity, once again, plays the leading role. As more and more stars formed, their collective gravitational pull began to draw them together into larger and larger structures.
It's like stars clumping together, forming cosmic clusters that eventually become galaxies.
That's a good way to think about it. These early galaxies were much smaller and less organized than the grand spiral and elliptical galaxies we see today. But they were the seeds from which our modern galactic landscape emerged.
So the universe was slowly transforming from a sea of darkness and scattered stars into a more structured cosmos filled with galaxies.
Yes. And not only were individual galaxies growing, but they were also interacting with each other, merging and colliding in a cosmic dance that continues to this day.
So those spectacular images we see of colliding galaxies, that's a process that's been happening for billions of years.
Exactly. Galactic mergers are a fundamental part of how galaxies evolve and grow. When galaxies collide, their gas clouds are compressed, triggering bursts of star formation. It's a chaotic, but also incredibly creative process.
Wow, it's amazing to think about these grand cosmic events shaping the universe around us. So we've gone from a tiny singularity to a universe filled with stars, galaxies, and all the elements that make up the world we know. It's been an incredible journey so far. But I'm curious, what happened next? Did the universe just settle into its current form, or are there more chapters to this story?
The universe is still evolving, still changing, still full of mysteries waiting to be unlocked. The story of the Big Bang is not over. It's still unfolding all around us. But I think that's a perfect place to take a break. We'll delve into the ongoing evolution of the universe and explore some of the mind-boggling possibilities for its ultimate fate in the final part of our deep dive.
I can't wait. This Big Bang stuff is truly mind-blowing. Listeners, join us next time as we explore what the future holds for our ever-expanding cosmos. Welcome back to our cosmic adventure. We've journeyed from the singularity through the formation of the first stars and galaxies. It's been an incredible ride, but I can't help but wonder, what's next for the universe? Where do we go from here?
That's the ultimate question, isn't it? The fate of the universe is one of the biggest mysteries in cosmology. And while we don't have all the answers, we have some pretty fascinating theories based on what we know about the universe's expansion. and the forces at play.
Okay, so let's talk about those theories. What are some of the possibilities for the universe's ultimate destiny?
One of the most widely discussed theories is called the Big Freeze, or heat death. This scenario is based on the idea that the universe will continue to expand indefinitely, and as it does, everything will become more and more spread out.
So kind of like a cosmic game of musical chairs, but the chairs keep getting further and further apart.
Exactly. As the universe expands, galaxies will drift apart, stars will burn out, and eventually all matter will be so dispersed that the universe will become a cold, dark, and incredibly empty place. Even black holes will eventually evaporate, leaving behind just a faint whisper of radiation.
That sounds a bit bleak, to be honest, a cold, dark, empty universe. Are there any other possibilities that are a little more, well, optimistic?
There are. Another theory, known as the Big Crunch, proposes a very different fate in this scenario. The expansion of the universe eventually slows down, stops, and then reverses. Gravity takes over, pulling everything back together in a cosmic collapse.
So instead of expanding forever, the universe would start shrinking, with everything heading back toward a singularity, kind of like a rewind of the Big Bang.
Exactly. The Big Crunch is essentially the Big Bang in reverse. It's a dramatic, and some might say poetic vision of the universe's end, a return to its origins.
That's certainly a more dramatic ending than a slow fade to darkness. Are there any other theories about the universe's fate?
There is another theory that has gained some traction in recent years, and it's perhaps the most mind-bending of them all, the Big Rip.
The Big Rip. Okay, I'm officially intrigued. What's that all about?
This theory hinges on the concept of dark energy, a mysterious force that seems to be driving the accelerated expansion of the universe.
Dark energy, that's still a big unknown, right?
It is. We know very little about dark energy, but its effects are undeniable. It seems to act as a sort of anti-gravity, pushing everything apart at an ever-increasing rate.
Okay, so how does dark energy factor into the Big Rip scenario?
In the Big Rip scenario, the strength of dark energy continues to increase over time. Eventually, its repulsive force becomes so powerful that it overcomes all other forces, even the fundamental forces holding matter together.
So not just galaxies drifting apart, but everything being torn asunder. Stars, planets, even atoms themselves.
Exactly. In the Big Rip scenario, the very fabric of space-time would be ripped apart, leaving behind, well, nothingness. It's a pretty dramatic and violent end to the universe.
Wow. That's a lot to take in. So we've got the Big Freeze, the Big Crunch, and the Big Rip. Three very different but equally mind-blowing possibilities for the universe's ultimate fate. Is there any way to know which one is most likely?
That's the challenge. Our understanding of dark energy and the long-term evolution of the universe is still evolving. Scientists are constantly gathering new data and refining their models. But for now, the ultimate fate of the universe remains an open question.
It's almost comforting to know that even with all our scientific advancements, there are still such grand mysteries out there. It's what keeps the spirit of exploration and discovery alive.
Absolutely. The universe is full of wonder. And the more we learn, the more we realize how much more there is to discover. It's a constant reminder of the power and beauty of the cosmos.
Well said. I want to thank you for taking us on this incredible journey through the Big Bang and beyond. It's been an eye-opening experience.
It's been my pleasure. I always enjoy diving into these cosmic questions with such an enthusiastic audience.
And I know our listeners have enjoyed it too. To all our Cosmos in a Pod fans out there, don't forget to subscribe, follow, and leave us a review. And as always, keep looking up and stay curious. The universe is waiting to be explored.